Tonight we're going to explore one of the most violent balancing acts in the entire universe. A neutron star is what's left after a massive star dies in a supernova explosion. It crams more mass than our entire Sun into a sphere roughly the size of a city. A single teaspoon of its material would weigh about 4 billion tons on Earth. Gravity at its surface is roughly 200 billion times stronger than what you feel standing on the ground right now. Every single moment, that gravity is trying to crush the star even further inward, and yet it doesn't collapse. Something inside is pushing back. Something invisible, something rooted in quantum mechanics and the strange behavior of matter under pressures we cannot recreate anywhere on Earth. But here's the part that will keep you thinking long after tonight. That resistance has a limit. Cross it, and the neutron star loses. Completely. Irreversibly. It becomes a black hole. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Right now, somewhere in this galaxy, there is an object roughly the size of Manhattan that contains more mass than our entire Sun. It is the crushed remains of a star that was once enormous. A star that burned through its fuel and then collapsed under its own weight with such force that the very atoms inside it were destroyed. Not broken apart in the way a molecule splits into atoms, destroyed in a more fundamental sense. The electrons were driven into the protons, merging them together, converting nearly everything into neutrons. What remains is a neutron star, a ball of matter so dense, so tightly packed, so utterly unlike anything on Earth, that even describing it accurately pushes our language to its limits. And yet, despite everything gravity has already done to this object, despite the fact that it has already crushed a stellar core down to a sphere roughly 20 kilometers across, gravity has not finished. Gravity never finishes. At this very moment, the gravitational force at the surface of that neutron star is hundreds of billions of times stronger than what you feel standing on the ground right now. And every fraction of that force is trying to compress the star further, trying to make it smaller, trying to force it past a point of no return where it would collapse into a black hole and vanish behind an event horizon forever. So here is the question that matters. Why hasn't it? What could possibly resist that kind of force? What is happening inside that object right now that prevents it from becoming a black hole? To answer that, we need to understand what a neutron star actually is, where it comes from, what it is made of, and what it is not. Because there are common misconceptions about neutron stars that sound reasonable, but lead you in exactly the wrong direction. And if you start from the wrong picture, the real physics becomes impossible to follow. A neutron star is the collapsed core of a massive star. Not just any star. Our Sun, for example, will never produce a neutron star. It doesn't have enough mass. When the Sun eventually exhausts its hydrogen fuel billions of years from now, it will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a much gentler form of stellar death. Neutron stars come from bigger, more violent origins. They come from stars that began their lives with at least 8 times the mass of the Sun, possibly more. These are the heavyweight stars of the galaxy, the kind that burn hot and fast and die young. During its life, a massive star is a nuclear furnace. Deep in its core, the temperature and pressure are so extreme that atomic nuclei are forced together, fusing lighter elements into heavier ones and releasing energy in the process. This energy is what keeps the star inflated. It generates outward pressure that balances the inward pull of gravity. As long as the star can keep fusing fuel, it survives. It maintains a delicate equilibrium, gravity pulling inward, energy pushing outward, neither side winning. The star begins by fusing hydrogen into helium in its core. When the hydrogen runs out, the core contracts and heats up until it's hot enough to start fusing helium into carbon and oxygen. When the helium runs out, the core contracts again and begins fusing carbon, then neon, then oxygen, then silicon. Each new fuel ignites at higher temperatures and lasts for a shorter time. Hydrogen burning can sustain a massive star for millions of years. Helium burning lasts maybe a few 100,000 years. Carbon burning lasts perhaps a few thousand years. By the time the star reaches silicon fusion, the final stage, it has only days left, sometimes just hours. This creates a layered structure in the star's interior, like the layers of an onion. Each shell contains a different element at a different stage of fusion. Hydrogen burns in the outermost layer, helium beneath that, carbon beneath that, and so on, deeper and deeper, hotter and hotter, until you reach the very center of the star, where the final product of silicon fusion accumulates. That product is iron, specifically iron 56, among the most tightly bound nuclei in nature. And this is where everything goes wrong. Every previous fusion reaction in the star's life released energy. That energy was what kept the star alive, what generated the outward pressure to hold back gravity. But iron is different. Fusing iron does not release energy. It requires energy. Iron sits at the bottom of the nuclear binding energy curve. You cannot extract energy by fusing it into anything heavier, and you cannot extract energy by splitting it into anything lighter. Iron is a dead end. So the core fills with iron, and no new energy source is available. The furnace goes cold. And without that energy pushing outward, gravity wins. Not slowly, not gently, catastrophically. The iron core, roughly the mass of our Sun, crammed into a volume about the size of Earth, collapses in on itself in less than a second. The outer layers of the core fall inward at speeds reaching a quarter of the speed of light. In that fraction of a second, the core compresses from something the size of Earth down to something the size of a city. The density increases by a factor of roughly 100 million. Material that was already incredibly hot and dense becomes something else entirely, something that does not exist anywhere else in the natural universe except inside neutron stars and in the first moments after the collapse of massive stellar cores. What happens next is a supernova. The infalling outer layers slam into the newly formed core, which has suddenly become incredibly rigid because of quantum mechanical effects we will explore shortly. That collision, combined with an enormous flood of particles called neutrinos pouring out of the core, sends a shockwave blasting outward through the rest of the star. The explosion is so powerful that for a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of stars. The outer layers of the star are blown into space at thousands of kilometers per second, scattering heavy elements across the cosmos. Elements that will eventually become part of new stars, new planets, and, if conditions are right, new life. But the core remains behind, compressed, crushed, transformed. What is left is a neutron star, and its properties are almost impossible to exaggerate. A typical neutron star has a mass between roughly 1.4 and about 2 times the mass of our Sun. All of that mass is compressed into a sphere approximately 20 kilometers across. That's roughly the distance you might drive in 15 minutes on a highway. Picture a city. Now picture that city weighing more than the Sun. That is a neutron star. The density is staggering. On average, the material inside a neutron star is around 250 trillion times denser than water. A single teaspoon of neutron star material, if you could somehow scoop it out and place it on Earth, would weigh roughly 4 billion tons. That is not a metaphor or an exaggeration for dramatic effect. That is what the physics demands. The matter is packed so tightly that the space between particles has essentially vanished. The surface gravity is equally extreme. Standing on the surface of a neutron star, if you somehow survived, you would weigh roughly 200 billion times more than you weigh on Earth. A human being weighing about 70 kilograms on Earth would weigh the equivalent of about 14 trillion kilograms on a neutron star's surface. Your body would be flattened into a layer thinner than a sheet of paper in a fraction of a second. Nothing resembling a solid structure could exist under that kind of gravitational force. The escape velocity, the speed you would need to leave the surface and never fall back, is roughly 150,000 to 200,000 kilometers per second. That is between roughly half and 2/3 the speed of light. For comparison, Earth's escape velocity is about 11 kilometers per second. To leave a neutron star, you would need to be moving at a significant fraction of the fastest speed anything in the universe can travel. Neutron stars also rotate, often extremely fast. When the core collapses from something the size of Earth down to something the size of a city, angular momentum is conserved. The same principle that makes an ice skater spin faster when she pulls her arms in applies to the collapsing core. A star that rotated once every few weeks can produce a neutron star that spins hundreds of times per second. Some neutron stars, called millisecond pulsars, rotate more than 700 times per second. The surface at the equator of such a star moves at a significant fraction of the speed of light, just from the rotation alone. Their magnetic fields are among the strongest in the known universe. A typical neutron star's magnetic field is roughly 1 trillion times stronger than Earth's. And a special class called magnetars can have magnetic fields 1,000 times stronger still, so intense that at close range they would distort the shapes of atoms and fundamentally alter the nature of chemistry itself. These are real objects. They exist right now in our galaxy. We have detected more than 3,000 of them, mostly as pulsars, neutron stars whose beams of radiation sweep past Earth like a lighthouse beam, producing regular pulses we can detect with radio telescopes. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student who noticed a strangely regular signal repeating every 1.34 seconds. The signal was so precise that for a brief time the team considered the possibility it might be an artificial transmission from another civilization. It was not. It was a neutron star, spinning with the precision of an atomic clock, announcing its existence across the galaxy. But the existence of neutron stars had been predicted decades earlier. In 1934, just 2 years after the neutron itself was discovered, 2 astronomers named Walter Baade and Fritz Zwicky proposed that when massive stars explode as supernovae, they might leave behind incredibly small, incredibly dense objects composed primarily of neutrons. At the time, many physicists considered the idea absurd. An object that dense seemed physically impossible. It took more than 30 years for the discovery of pulsars to prove them right. Now, there is a common way of thinking about neutron stars that is tempting but dangerously misleading. People sometimes describe a neutron star as a giant atomic nucleus. After all, an atomic nucleus is made mostly of protons and neutrons packed tightly together. A neutron star is made mostly of neutrons packed tightly together. They are both incredibly dense. The comparison seems natural. But a neutron star is not a giant nucleus, and treating it as one leads to serious misunderstandings about the physics. An atomic nucleus is held together by the strong nuclear force, the most powerful force in nature at short distances. Inside a nucleus, protons and neutrons attract each other through this force, which overcomes the electromagnetic repulsion between positively charged protons. The largest naturally occurring nucleus, uranium-238, contains 238 nucleons and is roughly 6 femtometers in radius, 6 quadrillionths of a meter. A neutron star contains roughly 10 to the power of 57 neutrons. That is not a slightly bigger nucleus, it is a fundamentally different kind of object. At nuclear density, the strong force behaves in complex ways. At the short distances inside a nucleus, it is attractive. But if you try to squeeze nucleons even closer, the strong force becomes repulsive. In a neutron star, the particles are not simply sitting together like protons and neutrons in a nucleus. They are compressed by gravity to densities that match and then exceed nuclear density. And at those densities, the behavior of matter is governed by a combination of quantum mechanics, nuclear physics, and gravitational physics that is far more complex than anything happening inside an ordinary nucleus. A neutron star has structure. It is not a uniform ball of the same material from surface to center. It is layered, and each layer is radically different from the one above it and the one below it. To understand what holds a neutron star up, you first need to understand what it is made of at each depth, because the physics that resists gravity changes as you travel inward. The outermost layer is a thin crust, perhaps a kilometer or two thick. The very surface of this crust is made of iron, the same element that ended the parent star's life. Below the surface, you find a lattice of increasingly heavy atomic nuclei, a crystalline structure somewhat similar in concept to the arrangement of atoms in a metal, though the conditions are far more extreme. The nuclei are organized into a rigid lattice held together by a sea of electrons flowing between them. This outer crust is the most normal material in the entire neutron star. It is matter you could, at least in principle, describe using the physics of ordinary atomic nuclei, just squeezed to extraordinary densities. But as you move deeper into the crust, the pressure increases relentlessly, and the nuclei change. Under the weight of the material above them, the nuclei become more and more neutron-rich. In ordinary matter, nuclei contain roughly equal numbers of protons and neutrons. But under the extreme pressures in a neutron star crust, the balance shifts. The electrons are forced into the nuclei, combining with protons to form additional neutrons. The nuclei become bloated with neutrons, containing far more neutrons than any nucleus found in nature on Earth. At a certain depth, roughly half a kilometer to a kilometer below the surface, the nuclei become so neutron-rich that they can no longer hold all their neutrons. Neutrons begin leaking out, dripping free from the nuclei and forming a fluid that surrounds them. This is called the neutron drip point, and it marks the boundary between the outer crust and the inner crust. Below this point, the matter is a strange mixture. Nuclei still exist, but they are enormous by nuclear standards, swollen with neutrons, and they are bathed in a free-flowing superfluid of neutrons that has oozed out of them. Nothing like this exists anywhere on Earth. Nothing like this can be created in any laboratory. It is a state of matter unique to neutron stars. And then, something truly bizarre happens. As you continue deeper through the inner crust, the pressure keeps rising, and the nuclei are squeezed closer and closer together. At a certain point, the nuclei begin to deform. They stop being roughly spherical. The pressure distorts them into elongated shapes. They stretch into rods. Then the rods merge into flat sheets. Then the sheets develop holes. Then the holes connect and the material inverts. with nuclear matter forming tubes and bubbles in a sea of neutrons rather than the other way around. Physicists have given these phases names borrowed from Italian cooking because the shapes resemble pasta. The spherical nuclei at lower densities are called gnocchi. The elongated rods are called spaghetti. The flat sheets are called lasagna. These names sound whimsical, almost comedic for something so extreme. But the physics is real and is supported by sophisticated computer simulations. The nuclear pasta phases represent a regime where matter is neither a collection of distinct nuclei nor a uniform sea of particles. It is something in between, a transitional state where the structure of matter itself is being dismantled by pressure, step by step, as gravity forces the material into configurations that minimize energy under these extraordinary conditions. The nuclear pasta layer is thought to be the strongest material in the universe. The lasagna phase in particular, those flat sheets of nuclear material stacked together, may have a breaking strain roughly 10 billion times greater than steel. If you tried to deform or shatter this material, it would resist with a tenacity that nothing on Earth could match. This incredible strength comes not from chemical bonds, which are far too weak to matter at these densities, but from the nuclear force itself, holding the sheets together in a configuration that is extraordinarily resistant to disruption. Below the nuclear pasta layers, you cross into the outer core. Here, the last remnants of nuclear structure dissolve. There are no more nuclei of any shape. There are no more lattices, no more rods, no more sheets. The matter has been squeezed past the point where individual nuclei can survive. What remains is a fluid, a dense, uniform sea of mostly free neutrons, with a smaller population of protons and electrons mixed in. This fluid is not like any liquid you have ever encountered. It is a quantum fluid, governed by the same exclusion principle we will discuss in detail shortly. The neutrons form a superfluid, a state of matter that flows without friction. The protons, though far fewer in number, form a superconductor, a state that allows electric currents to flow without resistance. These quantum states persist even at temperatures of hundreds of millions of degrees, because the relevant energy scales inside a neutron star are so extreme that what we consider extraordinarily hot is, by neutron star standards, essentially cold. And at the very center, in the inner core, the density is so extreme that nobody knows for certain what state matter takes. It might remain as neutrons. It might transition into exotic forms of matter involving particles called hyperons. Some physicists have proposed that at the highest densities, the neutrons themselves might dissolve into their constituent quarks, forming a quark soup unlike anything that exists anywhere else in nature. The internal structure of a neutron star is layered, complex, and deeply uncertain. A giant nucleus it is not. There is another misconception worth clearing up immediately, because it relates directly to the central question of what holds a neutron star up. In everyday experience, the things that resist compression are usually explained by pressure from heat. A balloon stays inflated because the hot air inside pushes outward. A star like the Sun stays inflated because the nuclear reactions in its core generate enormous heat, and that thermal energy creates pressure that resists gravity. You might naturally assume something similar is happening in a neutron star. You might think the neutron star is incredibly hot inside, and that heat is what holds it up. Neutron stars are indeed hot. A newly formed neutron star can have internal temperatures of hundreds of billions of degrees. But thermal pressure, the kind of pressure that comes from particles bouncing around due to their heat energy, is not what prevents a neutron star from collapsing. If you could somehow magically cool a neutron star to absolute zero, removing all thermal energy entirely, it would barely shrink at all. The pressure holding it up would remain almost unchanged. Thermal pressure is negligible compared to the forces actually at work inside a neutron star. This is a crucial point. The thing preventing a neutron star from becoming a black hole is not heat. It is not the ordinary kind of pressure you learn about in a basic physics class. It is something fundamentally different, rooted in quantum mechanics and the behavior of matter at densities that no laboratory on Earth can produce. To understand what that something is, it helps to first understand a simpler case. Before a neutron star forms, before the core collapse and the supernova, there is another kind of dead star that faces a similar problem but solves it in a related way. That object is a white dwarf. A white dwarf is what remains when a less massive star dies. Stars like our Sun, stars that are not heavy enough to explode as supernovae, end their lives by swelling into red giants and then shedding their outer layers, leaving behind a hot, dense core. That core is a white dwarf. It is roughly the size of Earth, perhaps 12,000 kilometers across, but it contains about the mass of the Sun. That makes it dense by everyday standards, around 1 million times denser than water, but nowhere near as dense as a neutron star. A white dwarf no longer has any nuclear fuel. There is no fusion happening in its core. No energy is being generated. And yet, it does not collapse under its own gravity. Something holds it up. That something is called electron degeneracy pressure, and it comes from a principle in quantum mechanics known as the Pauli exclusion principle. This principle states that no two identical fermions, a category of particles that includes electrons, protons, and neutrons, can occupy exactly the same quantum state at the same time. It is not a suggestion. It is not something that can be overcome with enough force, at least up to a point. It is a fundamental rule of the quantum world. In a white dwarf, the electrons are packed closely together by gravity. As the density increases, the electrons are forced into higher and higher energy states, because the lower energy states are already occupied. Each electron must have its own unique quantum state. As they are compressed, the only way to accommodate them is for them to move faster and faster, occupying states with higher and higher momentum. This creates a pressure, not from heat, not from collisions in the traditional sense, but from the quantum mechanical requirement that fermions cannot share states. This pressure pushes outward against gravity, and in a white dwarf, it wins. The star reaches an equilibrium and sits there, slowly cooling over billions of years, held up by the quantum nature of electrons. But there is a limit. In 1930, a young Indian physicist named Subrahmanyan Chandrasekhar, barely 20 years old and travelling by ship to England to begin his graduate studies, worked out the mathematics of this limit during the voyage. What he discovered would eventually earn him the Nobel Prize, though the result was controversial at the time and took decades to be fully accepted. Chandrasekhar showed that as a white dwarf becomes more massive, the electrons inside it must move faster and faster to generate enough degeneracy pressure. But there is a cosmic speed limit. Nothing can move faster than light. As the electrons approach the speed of light, they become relativistic, and their pressure becomes less effective at resisting further compression. The electrons are still pushing back, but they cannot push back fast enough. At a mass of about 1.4 times the mass of the Sun, gravity overwhelms even relativistic electron degeneracy pressure. This is the Chandrasekhar limit. Beyond it, no amount of electron degeneracy pressure can hold the star up. The electrons have given everything they can, and it is not enough. What happens next is exactly what you would expect. The white dwarf collapses. But it doesn't collapse into nothing. As the density climbs higher and higher, the electrons are squeezed so tightly against the protons that a nuclear reaction occurs. The electrons combine with the protons, producing neutrons and releasing neutrinos. This process is called electron capture, and it converts nearly all the protons and electrons in the core into neutrons. The identity of the matter changes. It goes from being a mixture of atomic nuclei and electrons to being overwhelmingly a fluid of neutrons. This is the moment of transformation. The core, held up by electron pressure much like a white dwarf, has now crossed a threshold. The electrons have been consumed. They no longer exist as free particles in sufficient numbers to provide their degeneracy pressure. The old source of support is gone, destroyed, absorbed into the neutrons. And the collapse continues until the material reaches nuclear density, roughly 230 trillion grams per cubic centimeter, and something new begins to resist. A new pressure, a new force. Not from electrons, because the electrons are gone. Not from heat, because thermal pressure at these densities is negligible. Not from ordinary mechanical resistance, because there is nothing ordinary about any of this. Something else is fighting back against gravity inside this newborn neutron star. Something that involves the quantum nature of neutrons themselves, the behavior of the strong nuclear force at incredibly short distances, and the properties of matter at densities so extreme that they do not exist naturally anywhere else in the observable universe. And understanding what that something is, understanding exactly how it works and where it fails, is one of the most important unsolved problems in all of physics. Because whatever that force is, it has a limit too. Just as the electrons eventually lost their battle against gravity at the Chandrasekhar limit, whatever holds up a neutron star can also be overwhelmed. Add enough mass, and the neutron star will lose. Add enough mass, and nothing in the known laws of physics can prevent the final collapse. Add enough mass, and the neutron star becomes a black hole. The question is how. The question is what exactly resists, and how much mass it takes to break that resistance. And the answer to that question connects to some of the deepest mysteries in modern physics. So far on this journey, we have arrived at a question. A neutron star sits at the edge of annihilation, compressed to densities that dwarf anything else in the observable universe. Gravity pulling inward with a force hundreds of billions of times stronger than what you feel on Earth. The old defense that worked for white dwarfs, electron degeneracy pressure, has been destroyed. The electrons have been absorbed into the protons, creating neutrons and removing the quantum pressure that once held the star up. The collapse has continued past the white dwarf stage, past the point where electron physics has any say in the matter. Something else had to step in. Something else had to resist gravity at densities where electrons no longer exist as a meaningful source of support. And something did. To understand what that something is, we need to return to a principle we touched on earlier, the Pauli exclusion principle. But this time, we need to look at it more carefully, because it is doing something far more dramatic inside a neutron star than it ever did inside a white dwarf. And even then, even after we understand what the exclusion principle contributes, we will discover that it is not enough to explain the full story. There is more going on inside a neutron star than any single quantum rule can account for. The Pauli exclusion principle was formulated in 1925 by the Austrian physicist Wolfgang Pauli. It is one of the foundational rules of quantum mechanics, and it divides every particle in the universe into two categories based on a quantum property called spin. Spin is not quite the same as the spinning of a top or a planet, though the analogy is sometimes used. It is an intrinsic quantum property, something a particle simply has, like mass or charge. Every particle has a specific spin value, and that value determines which of the two categories it belongs to. Particles with half-integer spin, meaning spin values like 1/2, 3/2, 5/2, and so on, are called fermions. Particles with integer spin, meaning spin values like 0, 1, 2, are called bosons. This distinction sounds technical, but it has profound consequences for the behavior of matter. Fermions obey the Pauli exclusion principle. No two identical fermions can occupy exactly the same quantum state at the same time and place. This is not a tendency, it is not a preference, it is an absolute rule, as fundamental as anything in physics. Electrons are fermions with a spin of 1/2. Protons are fermions with a spin of 1/2, and neutrons are fermions with a spin of 1/2. All three of the particles that make up ordinary matter are fermions. All three are subject to the exclusion principle. Bosons, on the other hand, do not obey this rule. Photons, which are particles of light, are bosons. You can pack as many photons as you want into the same quantum state. This is actually what makes a laser work. Millions of photons occupying the identical quantum state, all in lockstep. But you could never do this with electrons or neutrons. They refuse to share. They cannot be forced into the same state no matter how much pressure you apply. Now, in a white dwarf, it was the electrons that provided the degeneracy pressure. As gravity compressed the star, the electrons were forced closer together. But the exclusion principle prevented them from all settling into the same low-energy state. Instead, as more electrons were crammed into a smaller volume, they had to occupy higher and higher energy states, because the lower states were already taken. These higher energy electrons move faster. That motion creates pressure, an outward push against gravity, not because the electrons are hot, but because quantum mechanics forces them to be energetic. This is degeneracy pressure. In a neutron star, the electrons are mostly gone. They have been consumed by electron capture reactions, absorbed into protons to create neutrons. But the neutrons themselves are fermions. They have spin 1/2. They obey the Pauli exclusion principle just as strictly as electrons do. And inside a neutron star, there are an almost incomprehensible number of them, roughly 10 to the power of 57 neutrons crammed into a sphere 20 kilometers across. As gravity compresses the neutron star, the neutrons are forced closer and closer together. And just as the electrons did in a white dwarf, the neutrons resist. The exclusion principle demands that each neutron occupy its own unique quantum state. As the density increases, the available low-energy states fill up. The remaining neutrons are forced into progressively higher energy states. They must move faster and faster, not because they are being heated, but because there is simply no room in the lower energy levels. Those levels are already occupied. The quantum rules leave no alternative. This creates neutron degeneracy pressure. It is the same fundamental mechanism that held up the white dwarf, but now it is the neutrons rather than the electrons doing the work. And because neutrons are much more massive than electrons, roughly 1,839 times more massive, the physics plays out differently. Heavier particles generate stronger degeneracy pressure at the same density. This is one reason why a neutron star can resist gravitational forces far beyond what any white dwarf could survive. Let me try to make this more intuitive, because degeneracy pressure is a strange concept. It does not work like any pressure you encounter in daily life. When you pump air into a tire, the pressure comes from gas molecules bouncing around and colliding with the walls of the tire. The faster the molecules move, the higher the pressure. If you heat the air, the molecules move faster and the pressure increases. If you cool the air, the molecules slow down and the pressure drops. This is thermal pressure, and it depends entirely on temperature. Degeneracy pressure is fundamentally different. Imagine a concert hall with numbered seats. Every seat is unique. You can only sell as many tickets as there are seats. As more people arrive, the available seats fill up. The last arrivals are forced into the highest, most remote seats, far from the stage. They didn't choose those seats. They were forced into them because every closer seat was already taken. Even if the temperature in the hall dropped to absolute zero, even if everyone stopped moving entirely in a thermal sense, they would still be in their seats. The seats don't disappear when the temperature drops. The occupancy is determined by the number of people and the number of available states, not by the temperature. In a neutron star, the neutrons are the people and the quantum states are the seats. Gravity keeps cramming more neutrons into a smaller volume, but the exclusion principle says each neutron must have its own seat. As the volume shrinks, the seats get rearranged into higher and higher energy levels. The neutrons sitting in those high energy states are moving fast, incredibly fast, and that motion generates pressure. But it has nothing to do with heat. It would exist even at absolute zero. It is a consequence of quantum statistics, a pressure that comes from the fundamental nature of fermions rather than from thermal energy. This pressure is enormous. Inside a neutron star, neutron degeneracy pressure generates forces that can resist hundreds of billions of times Earth's surface gravity. It is one of the most powerful forms of pressure in the universe, and it plays a critical role in preventing the neutron star from collapsing into a black hole. But here is where the story becomes far more complicated than most popular accounts suggest. Because neutron degeneracy pressure alone does not fully explain what holds up a neutron star. If you built a mathematical model of a neutron star using only degeneracy pressure and nothing else, treating the neutrons as a simple, non-interacting gas of fermions, you would get a maximum mass for a neutron star that is significantly lower than what we actually observe. The model would predict that neutron stars cannot be heavier than roughly 0.7 solar masses. But we have observed neutron stars with masses of 2 solar masses and possibly higher. Something else must be contributing. That something else is the strong nuclear force. The strong nuclear force is the most powerful force in nature at the distances relevant to nuclear physics. It is what holds protons and neutrons together inside an atomic nucleus. Without it, nuclei would fly apart because the protons, all positively charged, would repel each other electromagnetically. The strong force overcomes that repulsion and binds the nucleons together. But the strong force is not simple. It does not behave like gravity or electromagnetism, forces that get steadily weaker with distance and follow clean mathematical laws. The strong force has a complicated relationship with distance that makes it unlike anything else in physics. At relatively large separations, larger than about 2 femtometers, the strong force between 2 nucleons is negligible. They barely feel each other. At intermediate distances, roughly between 1 and 2 femtometers, the strong force becomes powerfully attractive. This is the range that holds nuclei together. The nucleons pull toward each other with tremendous force. But at very short distances, below about 0.5 femtometers, something dramatic happens. The strong force becomes repulsive. Instead of pulling nucleons together, it pushes them apart. The closer you try to force 2 nucleons, the harder this repulsive core pushes back. It acts like a wall. You can compress nucleons to a certain point, but if you try to push them closer than this characteristic distance, the strong force fights you with enormous intensity. To understand why this repulsive core matters so much, imagine pushing 2 powerful magnets together. At a moderate distance, you can feel them pulling toward each other, snapping together eagerly. But now imagine that at the very center of each magnet, there is a small, incredibly hard rubber ball. You can bring the magnets close. You can feel them attract. But once the rubber balls touch, you cannot push them any closer. The attraction brought them together, but the hard core prevents them from merging. No matter how hard you squeeze, the rubber balls resist. That hard, incompressible core is analogous to the repulsive core of the strong nuclear force. The strong force attracts nucleons at moderate distances, pulling them into the tight configurations we see inside atomic nuclei. But below a certain separation, something physically different takes over. The interaction becomes fiercely repulsive, creating a floor beneath which the particles simply cannot be compressed without overcoming an enormous energy barrier. Inside an ordinary atomic nucleus, this repulsive core does not matter very much. The nucleons sit comfortably at the attractive distance, roughly 1 femtometer apart, and the repulsive core at shorter range is never tested. The nucleons never get close enough for it to activate. But inside a neutron star, the story is completely different. Gravity has compressed the matter so severely that the neutrons are closer together than they would be inside any normal nucleus. They are being forced into the range where the repulsive core dominates, and it is pushing back with a vengeance. This repulsive core of the strong nuclear force is absolutely critical to the physics of neutron stars. Inside a neutron star, especially deep in the core, where densities exceed the density of an atomic nucleus, the neutrons are packed so tightly that they are within this repulsive range. They are closer together than neutrons inside a normal nucleus. The repulsive component of the strong force is actively pushing back against gravity, adding a layer of resistance on top of what neutron degeneracy pressure provides. Think of it this way. The Pauli exclusion principle provides a kind of quantum mechanical flaw. It prevents the neutrons from occupying the same states, forcing them into higher energy configurations and generating pressure. But the strong nuclear force adds a wall. Even if quantum mechanics alone would allow the neutrons to get a little closer by rearranging their states, the repulsive core of the strong force says no. You cannot compress further without overcoming this nuclear repulsion. The two effects work together. Quantum statistics and nuclear forces collaborate against gravity, and this collaboration is what allows neutron stars to exist at masses well above what simple degeneracy pressure would permit. The observed 2 solar mass neutron stars would be impossible without the contribution of nuclear interactions. Degeneracy pressure gets the star partway there. The strong force provides the additional stiffness needed to support the heavier neutron stars we actually see. But describing the strong force as simply attractive at one distance and repulsive at another is itself a simplification. The reality inside a neutron star is far messier. The strong nuclear force between nucleons is not a fundamental force in the way we usually think of forces. It is a residual effect. The truly fundamental strong force, described by the theory called quantum chromodynamics, acts between quarks, the smaller particles that make up protons and neutrons. Each proton and each neutron contains 3 quarks bound together by particles called gluons. The force between quarks carried by gluons is extraordinarily powerful and has strange properties. It gets stronger as quarks move farther apart and weaker as they get closer. This is called asymptotic freedom, and its discovery earned a Nobel Prize in 2004. The force between 2 neutrons, the force we've been discussing, is not the fundamental quark-gluon interaction itself. It is a residual effect, similar to how the van der Waals force between 2 neutral atoms is a residual effect of the electromagnetic force between their charged components. The neutron-neutron interaction is mediated by the exchange of particles called pions and other mesons, which are themselves made of quarks and antiquarks. This makes the neutron-neutron force incredibly complex to calculate from first principles. You are not dealing with a clean, simple law. You are dealing with a force that arises from the messy, complicated interactions of quarks and gluons inside composite particles, filtered through the exchange of other composite particles between them. At ordinary nuclear densities, around 230 trillion grams per cubic centimeter, physicists have a reasonable understanding of how this force behaves. Decades of experiments with atomic nuclei and particle accelerators have constrained the neutron-neutron interaction at these densities. We know roughly how stiff or how soft matter is at nuclear density. But inside a neutron star, particularly deep in the core, the density exceeds ordinary nuclear density by factors of 2, 3, 5, possibly even 10. And at these supranuclear densities, our experimental knowledge essentially vanishes. No laboratory on Earth can create and sustain matter at these densities. The closest we come is in heavy ion collision experiments at facilities like the relativistic heavy ion collider and the Large Hadron Collider, where gold or lead nuclei are smashed together at nearly the speed of light, briefly creating tiny droplets of ultra-dense matter. But these collisions produce matter that is extremely hot and exists for only a fleeting instant before flying apart. The matter inside a neutron star is relatively cold by comparison and exists in a stable, long-lived state. The conditions are different enough that translating laboratory results directly to neutron star interiors is fraught with uncertainty. This means that when we try to calculate the pressure inside a neutron star at densities 2 or 3 times nuclear density, we are extrapolating far beyond our experimental knowledge. Different theoretical models of the strong force, all of which agree at ordinary nuclear density, can give wildly different predictions at higher densities. Some models predict that matter remains relatively stiff at supranuclear densities, meaning it provides a lot of resistance to compression. Other models predict it becomes softer, providing less resistance. The difference is not academic. It directly determines how massive a neutron star can be before it collapses into a black hole. And the complications do not stop there. At the extreme densities in a neutron star's core, the very identity of the particles present might change. We have been talking about neutrons as though they are the only important players, but in reality, a neutron star's core is not made entirely of neutrons. Even in the outer core, roughly 5 to 10% of the particles are protons and electrons. The ratio of neutrons to protons is determined by an equilibrium between nuclear reactions that convert one into the other. This equilibrium, called beta equilibrium, ensures that the star settles into a state where no net conversion is happening. But the presence of protons and electrons, even as a minority, affects the pressure and the stiffness of the matter. At higher densities, deeper in the core, other particles might appear, particles that do not exist in ordinary matter. These include hyperons, which are heavier relatives of neutrons and protons that contain at least one strange quark instead of the ordinary up and down quarks. Hyperons are unstable in a laboratory. They decay in a tiny fraction of a second, but inside a neutron star, the density is so extreme that the energy cost of maintaining a hyperon becomes lower than the energy cost of forcing yet another neutron into a high-energy state dictated by the exclusion principle. In other words, it becomes energetically favorable for some neutrons to convert into hyperons rather than occupying the increasingly expensive high-energy neutron states. Think of it in terms of the concert hall analogy we used earlier. The neutrons are audience members, and the quantum states are seats. Gravity keeps forcing more and more neutrons into the hall, the lower seats filled long ago. Every new arrival must climb higher and higher into the balconies, occupying more energetic, more expensive states. The pressure generated by all those high-energy neutrons is what holds the star up. But now imagine a second concert hall opens next door with its own empty seats. This second hall represents the hyperon states. Some neutrons can convert into hyperons and move into the new hall, where there are plenty of low-energy seats available. This relieves the overcrowding in the neutron hall. Fewer neutrons need to sit in the expensive high-energy balcony seats. This sounds like good news for the star at first, a way to relieve the pressure of overcrowded neutron states. But it has a dangerous consequence. If hyperons appear, they provide a new set of low-energy quantum states for baryons to occupy. This softens the matter. It reduces the overall pressure, and lower pressure means less resistance to gravity. The appearance of hyperons could significantly reduce the maximum mass a neutron star can support. And this is where the danger becomes clear. The relief that hyperons provide is precisely the problem. By draining neutrons out of their high-energy states and allowing them to relax into lower-energy hyperon states, the total pressure inside the star drops. The the star's ability to resist gravity weakens. It is as though the foundation of a building were made of compressed springs, and someone started removing springs and replacing them with softer cushions. The building might feel more comfortable, but it can no longer support as much weight. And inside a neutron star, the weight it needs to support is its own mass amplified by general relativistic gravity. Any reduction in pressure is a step toward collapse. This creates what physicists call the hyperon puzzle. If hyperons appear in the core of a neutron star, the predicted maximum mass drops. In some calculations, it drops below 2 solar masses. But we have observed neutron stars at or above 2 solar masses, so either hyperons do not appear when our models say they should, or something else provides additional pressure to compensate. Perhaps the interactions between hyperons at these extreme densities are different from what current models predict. Perhaps the hyperon-neutron and hyperon-hyperon forces are stiffer than we think, providing enough repulsion to make up the difference. Perhaps a three-body interaction, an effect that emerges only when 3 particles are crammed together simultaneously, generates additional repulsion that the simpler 2-body calculations miss entirely. Or perhaps hyperons do not appear at all, and the models that predict them are wrong. This is an unsolved problem, and it illustrates just how uncertain the physics of neutron star interiors truly is. And then, there is an even more extreme possibility. At the very highest densities in the innermost core, the neutrons themselves might dissolve. Remember, each neutron is made of 3 quarks bound together by gluons. Under normal conditions, quarks are permanently confined inside nucleons. You cannot isolate a single quark. If you try to pull one out, the energy you invest creates new quarks and antiquarks before the original quark can escape. This confinement is one of the defining features of the strong force. But at extremely high densities, theory suggests that confinement might break down. The neutrons could dissolve, their quarks spilling out into a continuous sea of free quarks and gluons. This state of matter is called quark matter, or quark-gluon plasma. If the very center of a neutron star contains quark matter, the properties of that material, its pressure, its stiffness, its resistance to compression, would be governed by the interactions between individual quarks and gluons, rather than by the interactions between neutrons. The physics would change fundamentally. The transition from neutrons to free quarks would be unlike anything we observe in everyday matter, but it is not without analogy. Think of ice melting into water. At low temperatures, water molecules are locked into a rigid crystalline structure. Each molecule is bound to its neighbors in a fixed lattice. The material is solid, structured, and orderly. But raise the temperature and the bonds break. The molecules come free and flow as liquid. The fundamental constituents are the same, water molecules, but their collective behavior changes completely. Something similar might happen inside a neutron star's deepest core. At densities a few times higher than nuclear density, the neutrons are intact, bound states of 3 quarks each. But at some critical density, the boundaries between individual neutrons might dissolve. The quarks that were confined inside separate neutrons start overlapping so much that it no longer makes sense to speak of individual neutrons at all. The matter transitions from a collection of distinct neutrons to a continuous fluid of quarks. The constituents are the same, quarks, but the way they organize changes profoundly. Some models predict that quark matter is stiffer than hadronic matter, the matter made of neutrons and protons. If that is the case, a quark matter core would actually help support the star, allowing heavier neutron stars to exist. Other models predict quark matter is softer, which would lower the maximum mass. Still other models suggest that the transition from hadronic matter to quark matter might be smooth, a gradual crossover rather than a sharp boundary. Others predict a sharp phase transition, like water freezing into ice, with sudden changes in density and pressure at a specific depth inside the star. The predictions depend on theoretical assumptions about quantum chromodynamics at densities where the theory becomes incredibly difficult to solve. This is the reality of neutron star physics. The object is held up not by any single mechanism, but by a combination of effects that are all tangled together. Neutron degeneracy pressure provides a foundation. The repulsive core of the strong nuclear force adds essential stiffness. The interactions between all the particles present, neutrons, protons, electrons, and possibly hyperons and free quarks, contribute to the total pressure. And all of these contributions depend on the density, which varies enormously from the outer crust to the innermost core. At the surface, the density is similar to what you find in ordinary materials. At the center, it can exceed the density inside an atomic nucleus by a factor of 5 or more. The physics changes continuously as you move deeper into the star, passing through regimes where different effects dominate. There is another subtlety that matters. We have been talking about pressure as though it is the only thing resisting gravity. In Newtonian physics, that would be essentially correct. Pressure pushes outward, gravity pulls inward, and the star is in equilibrium when the two balance. But neutron stars are so dense and their gravity so strong that Newtonian physics is not accurate enough. You need Einstein's general theory of relativity to describe them correctly. And general relativity introduces a complication that does not exist in Newtonian gravity. In Einstein's theory, pressure itself contributes to gravity. This sounds paradoxical. Pressure is what resists gravity, but pressure also makes gravity stronger. The reason is that in general relativity, it is not just mass that curves space-time and creates gravitational attraction. Energy in all its forms contributes, including the energy associated with pressure. A neutron star with higher internal pressure has a stronger gravitational field than a neutron star with the same mass but lower pressure, all else being equal. This creates a kind of feedback loop. Gravity compresses the star. The compression increases pressure. But the increased pressure also increases the gravitational field, which demands even more pressure to resist. At moderate densities, this feedback is manageable. The pressure wins and the star stabilizes. But at very high densities, near the maximum mass a neutron star can support, this feedback becomes significant. The pressure is working against itself. Every bit of additional support it provides also strengthens the force it is fighting against. This relativistic effect is one of the reasons why the maximum mass of a neutron star is lower than you might naively expect from Newtonian calculations. General relativity makes the balance harder to maintain. This means that the internal physics of a neutron star cannot be separated from the gravitational theory that describes it. The quantum mechanics of fermions, the nuclear physics of the strong force, and the general relativistic description of gravity are all intertwined. You cannot understand one without the others. A neutron star is a place where three of the deepest frameworks in all of physics, quantum mechanics, nuclear physics, and general relativity, all meet and all matter simultaneously. It is one of the very few objects in the universe where this is true. And this is precisely why neutron stars are so important to physics. They are not just exotic curiosities. They are natural laboratories that test our understanding of matter under conditions we cannot reproduce on Earth. Every observation of a neutron star, its mass, its radius, its rotation rate, its response to tidal forces during a merger, every one of these measurements carries information about the physics happening deep inside. Information about the strong force at supranuclear densities. Information about whether hyperons or free quarks exist in the core. Information about how matter behaves under pressures that no experiment on Earth can achieve. The object that sits at the heart of all this, the neutron star, is not held up by one simple thing. It is held up by a conspiracy of quantum mechanics and nuclear physics, with help and hindrance from general relativity. The Pauli exclusion principle forces neutrons into high-energy states, generating degeneracy pressure. The repulsive core of the strong force adds stiffness, preventing further compression beyond a certain point. The interactions between all the particles present modify the total pressure in ways that depend sensitively on the density and composition. And general relativity simultaneously strengthens the gravitational field that all of this pressure must resist. This balance is real. It is happening right now inside every neutron star in the galaxy. But it is not permanent. It is not guaranteed. The balance depends on the mass of the star. For a neutron star well below the maximum mass, the balance is comfortable. The quantum and nuclear pressures have plenty of room to spare. The star could absorb additional mass and still survive. But as the mass increases, the balance tightens. The internal pressures rise, but so does the gravitational field. And general relativity ensures that the gravitational field rises faster than a simple Newtonian calculation would suggest. The margin between survival and collapse narrows. Somewhere, at some specific mass, the margin disappears entirely. No amount of quantum pressure, no amount of nuclear repulsion, no rearrangement of particles or phase transition to a different state of matter can generate enough outward force to counteract the inward pull of gravity amplified by the energy of the pressure itself. And at that point, the balance breaks. The neutron star collapses. And what lies beyond that collapse is something from which nothing, not light, not information, not matter, can ever return. A black hole. But what determines that critical mass? What controls where the balance fails? That depends on something we have not yet discussed directly, something that encodes everything about how pressure relates to density inside ultra-dense matter. Physicists call it the equation of state. And it is the single most important thing about neutron stars that we do not know. We have spent a great deal of time building up a picture of what is happening inside a neutron star. Neutron degeneracy pressure, the repulsive core of the strong nuclear force, the possible appearance of exotic particles, the relativistic feedback loop where pressure itself strengthens gravity. All of these effects are real, and all of them contribute to the internal resistance that prevents a neutron star from collapsing into a black hole. But here is the problem. We know these effects exist. We know, in broad terms, how they work. What we do not know is precisely how strong each contribution is at the extreme densities found deep inside the core. And without knowing that, we cannot answer the single most important question in neutron star physics. How much mass can a neutron star support before it collapses? Everything we have discussed so far funnels into a single concept, one relationship, one function that, if we could determine it exactly, would unlock essentially everything about the interior physics of neutron stars. Physicists call this the equation of state. The equation of state is, in its simplest form, the relationship between pressure and density inside a material. It tells you this: if matter is compressed to a particular density, how much pressure does it exert? If you squeeze it to twice that density, how much more pressure does it produce? The equation of state is the rule that connects how tightly matter is packed with how hard it pushes back. You already have intuitive experience with equations of state, even if you have never heard the term. Think about air inside a sealed container. If you compress the air by pushing a piston inward, the pressure increases. Push harder, compress more, and the pressure rises further. The relationship between how much you compress the air and how much pressure it exerts back against the piston is the equation of state of air. For an ideal gas at constant temperature, this relationship is straightforward. Double the density and the pressure doubles. It is a simple, linear connection. Now think about something less compressible: water. If you try to compress water, the pressure rises much more steeply. Water resists compression far more strongly than air does. you need enormous force to reduce the volume of water by even a small amount. The equation of state of water is much stiffer than the equation of state of air. The word stiff here has a precise meaning. A stiffer equation of state means that pressure increases more rapidly as density increases. The material pushes back harder for each additional increment of compression. A softer equation of state means pressure rises more slowly. The material gives way more easily. Now replace air and water with the material inside a neutron star. The question becomes the same. As gravity compresses the material to higher and higher densities, how much pressure does it generate? Does the pressure rise steeply, resisting compression aggressively, or does it rise gently, allowing gravity to compress the material more easily? This is not an abstract question. The answer determines the fate of the star. If the equation of state of ultra-dense matter is stiff, meaning pressure increases sharply with density, then the material inside the neutron star pushes back hard against gravity. A stiff equation of state allows the star to support more mass before the internal pressure is overwhelmed. Stiff matter makes for bigger, heavier neutron stars that can survive at higher masses without collapsing. If the equation of state is soft, meaning pressure increases more gradually with density, then the material gives way more easily. Gravity can compress the star more tightly. A soft equation of state means the star reaches its breaking point at a lower mass. The maximum sustainable mass is smaller. Collapse into a black hole happens sooner. The equation of state also determines the physical size of a neutron star. A stiffer equation of state produces a larger star at a given mass, because the internal pressure holds the material at a greater radius. A softer equation of state produces a more compact star, because the material is squeezed more tightly. So the equation of state controls both the maximum mass and the radius. Two quantities that, if measured precisely, would tell us an enormous amount about the behavior of matter under the most extreme conditions in the universe. The reason this matters so deeply is that the equation of state of ultra-dense matter is unknown. We do not have it. Nobody does. It is the single biggest unsolved problem in neutron star physics, and arguably one of the most important unsolved problems in all of nuclear physics. The difficulty is fundamental. To determine the equation of state, you need to understand how matter behaves at densities several times higher than the density inside an atomic nucleus. And as we discussed earlier, no experiment on Earth can create and sustain matter at these densities. Heavy ion collision experiments produce tiny fireballs of ultra-dense matter, but these fireballs are extremely hot and last for an unimaginably brief instant before flying apart. The matter inside a neutron star is comparatively cold and persists for billions of years. The conditions are so different that translating laboratory results to neutron star physics is incredibly challenging. Theoretical calculations from first principles are equally difficult. The fundamental theory of the strong force, quantum chromodynamics, is mathematically intractable at the densities relevant to neutron star cores. The equations can be solved numerically on supercomputers at zero density and very high temperature, but at the finite densities and relatively low temperatures inside a neutron star, the standard computational techniques fail. Physicists must rely on approximate models, effective theories, and educated extrapolations from what they know at lower densities. Different models, all consistent with known experimental data, predict different equations of state, and those different equations of state lead to dramatically different predictions for the maximum mass and radius of neutron stars. This is why the exact maximum mass of a neutron star is uncertain. It is not because physicists are bad at calculations. It is because the fundamental input to the calculation, the equation of state, is not known. The uncertainty in the equation of state translates directly into uncertainty in the maximum mass. So what do we know about the maximum mass? We know there is one. This was established in 1939, less than a decade after Chandrasekhar showed that white dwarfs have a mass limit. In that year, J. Robert Oppenheimer, the same physicist who would later lead the Manhattan Project, together with George Volkoff, published a landmark calculation. Building on earlier work by Richard Tolman, they used Einstein's general theory of relativity to derive the equations governing the structure of a star supported by degeneracy pressure. These equations, now called the Tolman-Oppenheimer-Volkoff equations, describe how pressure and density must vary throughout the interior of a neutron star in order for the star to be in equilibrium, with the inward pull of gravity exactly balanced by the outward push of internal pressure at every point. The Tolman-Oppenheimer-Volkoff equations are the relativistic generalization of the equations that describe the structure of any self-gravitating sphere. They account for everything general relativity demands: the curvature of spacetime caused by the mass and energy inside the star, the fact that pressure itself contributes to the gravitational field, the way time flows differently at different depths within the star because of the varying strength of gravity. All of these effects are encoded in the equations. When you solve the Tolman-Oppenheimer-Volkoff equations for a given equation of state, you get a family of possible neutron star models, each with a specific mass and radius. You can start with a low central density and calculate a low-mass neutron star, then increase the central density and calculate a more massive one. As you keep increasing the density, the mass increases, but not forever. At some point, increasing the central density further actually causes the mass to decrease. This is the turning point. The maximum mass in that family of solutions is the Tolman-Oppenheimer-Volkoff limit for that particular equation of state. Beyond this limit, no stable equilibrium exists. There is no configuration of matter, no arrangement of pressure and density that can hold the star up. If the mass exceeds this limit, the star must collapse. Nothing can prevent it. Not degeneracy pressure, not nuclear forces, not any known form of matter. The collapse proceeds all the way to a black hole. The key phrase there is, for that particular equation of state. Different equations of state give different Tolman-Oppenheimer-Volkoff limits. A stiff equation of state yields a higher maximum mass. A soft one yields a lower maximum mass. The true Tolman-Oppenheimer-Volkoff limit of nature, the actual maximum mass a neutron star can have in our universe, depends on which equation of state is the correct one. And since we do not know the correct equation of state, we do not know the exact limit. What we can say is that the limit almost certainly lies above about 2 solar masses, and probably below roughly 2.5 solar masses. The lower bound comes directly from observation. We have already discovered neutron stars with masses near and above 2 solar masses, so any equation of state that predicts a maximum mass below that value is ruled out. Nature has already eliminated it. If the true limit were lower, those heavy neutron stars simply could not exist. The upper bound comes from theoretical constraints. Equations of state that are too stiff tend to violate fundamental principles, such as the requirement that the speed of sound inside the material cannot exceed the speed of light. This causal limit puts an upper bound on how stiff the equation of state can be, and therefore puts an upper bound on how heavy a neutron star can get. The comparison with the Chandrasekhar limit for white dwarfs is instructive. The Chandrasekhar limit is approximately 1.4 solar masses, and it is known with extraordinary precision. The reason for this precision is that the equation of state of white dwarf material is well understood. White dwarfs are supported by electron degeneracy pressure, and the electrons in a white dwarf behave essentially as a free, non-interacting gas of fermions. The physics is clean. The interactions between particles are weak and well characterized. You can calculate the equation of state from first principles with great accuracy, plug it into the structure equations, and get a precise answer. The Tolman-Oppenheimer-Volkoff limit does not enjoy this luxury. The neutrons inside a neutron star are not a free, non-interacting gas. They interact strongly with each other through the nuclear force. Those interactions are complex, poorly constrained at supranuclear densities, and potentially involve phase transitions to exotic states of matter. The equation of state is not something you can calculate cleanly from first principles. It depends on the messy, complicated, poorly understood behavior of the strong force at energy scales and densities where our theories struggle. This is why the exact maximum mass remains uncertain. But the uncertainty has been narrowing, and the way it has narrowed is one of the most exciting stories in modern astrophysics. The most powerful constraints on the equation of state come from observations of the heaviest known neutron stars. Every time astronomers discover a neutron star with a reliably measured mass near or above 2 solar masses, it eliminates a swathe of possible equations of state. Any model that predicts a maximum mass below the observed value is wrong. It does not matter how elegant the theory is or how well it fits other data. If it cannot produce a neutron star as heavy as one that actually exists, it is excluded. The first major breakthrough came in 2010, when a team led by Paul Demarest measured the mass of a neutron star in a binary system with a white dwarf companion. The neutron star was a millisecond pulsar, spinning roughly 300 times per second with extraordinary regularity. The measurement used a technique called the Shapiro delay. When pulsar signals pass close to the white dwarf companion, the curvature of space-time around the companion causes the signals to arrive slightly late. By measuring this delay with extreme precision, astronomers could determine the masses of both the pulsar and its companion. The result was a neutron star mass of 1.97 solar masses, with an uncertainty small enough to make the measurement robust. This single observation sent shockwaves through the nuclear physics community. A mass of nearly 2 solar masses was higher than many models had predicted was possible. Several popular equations of state, particularly those incorporating high porons or certain types of quark matter that softened the equation of state significantly, predicted maximum masses below 1.97 solar masses. Those models were immediately in trouble. Either they were wrong about the presence of hyperons, wrong about how those particles interact at extreme density, or missing some additional source of pressure that compensated for the softening. More discoveries followed. In 2013, another neutron star in a binary system was measured at approximately 2.01 solar masses using a similar technique. Then, in 2019, a team led by Heva Kromati announced a measurement of a different millisecond pulsar that yielded a mass of approximately 2.14 solar masses, with uncertainties placing the value potentially even higher. A subsequent refined analysis by Emmanuel Fonseca and colleagues in 2021 placed the mass at approximately 2.08 solar masses, with tighter error bars. These measurements confirmed that 2 solar mass neutron stars are not flukes. They are real, and any viable equation of state must accommodate them. Each of these observations acts like a filter. The landscape of possible equations of state, which was once vast, has been progressively narrowed. Soft equations of state that cannot support 2 solar masses are eliminated. What remains must be stiff enough to reach at least that mass, while still being consistent with other observations and theoretical constraints. But mass measurements are not the only tool available. The radius of a neutron star also carries information about the equation of state. A stiffer equation of state produces larger neutron stars at a given mass. A softer one produces smaller, more compact ones. If you can measure both the mass and the radius of a neutron star simultaneously, you can place much tighter constraints on the equation of state than either measurement alone would provide. Measuring the radius of a neutron star is enormously difficult. These objects are only about 20 kilometers across, and even the nearest known neutron stars are hundreds of light years away. You cannot simply photograph a neutron star and measure its size. Instead, astronomers use indirect methods, analyzing the X-ray emission from the surface of the star and using sophisticated models to infer the radius. An instrument called NISA, the Neutron Star Interior Composition Explorer, was installed on the International Space Station in 2017 precisely for this purpose. NISA is a collection of X-ray telescopes designed to observe the thermal emission from the surfaces of neutron stars with unprecedented precision. By carefully modeling how the X-rays are emitted and how they are bent by the intense gravitational field near the surface, the NISA team has been able to estimate the radii of several neutron stars. The results, published in a series of papers beginning in 2019 and continuing through the early 2020s, suggest that a typical neutron star with a mass of about 1.4 solar masses has a radius of roughly 12 to 13 kilometers. This is an extraordinary result. It tells us that the equation of state is moderately stiff, not too soft to support the observed masses, but not extremely stiff either. The matter inside a neutron star pushes back firmly against gravity, but not with unlimited ferocity. These radius measurements, combined with the mass measurements of the heaviest known neutron stars, are beginning to paint a coherent picture. The equation of state of dense matter must be stiff enough to support at least 2.08 solar masses, but it must also produce radii in the range of roughly 12 to 13 kilometers for canonical mass neutron stars. This combination eliminates a large number of theoretical models and significantly narrows the range of possibilities. There is something deeply remarkable about this entire enterprise. We are using observations of objects that are light years away, objects we can never visit, objects we can never bring into a laboratory, to determine the fundamental properties of matter at densities that no terrestrial experiment can achieve. The neutron star itself is the experiment. Its mass and radius are the data. And the equation of state, the relationship between pressure and density that governs the behavior of matter at the most extreme conditions in the universe, is what we are trying to extract from that data. This is observational nuclear physics, conducted with telescopes rather than accelerators. And it works. The constraints from neutron star observations are now competitive with, and in some cases stronger than, the constraints from laboratory experiments. Nature has given us a laboratory we could never build, and we are learning to read its results. There is another way to constrain the equation of state that became available only recently, and it involves gravitational waves. We will discuss this in detail shortly, but it is worth mentioning here because it connects directly to the equation of state. When two neutron stars orbit each other in a tight binary system and spiral inward toward a collision, they raise tidal distortions on each other. Each star's gravity deforms the shape of the other, stretching it slightly. The amount of deformation depends on how compressible the material inside the star is. A star with a stiff equation of state deforms more easily because it is larger and less centrally concentrated. A star with a soft equation of state deforms less because it is more compact and more tightly bound. This tidal deformation affects the gravitational waves emitted during the final stages of the in-spiral. The waves carry an imprint of how much each star was distorted, and from that imprint you can extract information about the equation of state. This is an entirely independent method from mass or radius measurements, and it provides complementary constraints. The first detection of gravitational waves from a neutron star merger, observed in 2017, provided the first such constraint. More detections will tighten it further. Let me take a step back and put all of this in perspective. What we are really doing when we study the equation of state is trying to answer a question that sounds simple but is extraordinarily deep. What happens to matter when you squeeze it as hard as the universe allows. At low densities, we know the answer. Matter forms atoms, molecules, crystals, liquids, gases. At higher densities, atoms are ionized into plasma, as inside the Sun. At still higher densities, electrons are forced into nuclei, merging with protons to form neutrons, as in the collapse that creates a neutron star. But at even higher densities, in the deepest cores of the heaviest neutron stars, what happens? Do the neutrons persist? Do they dissolve into quarks? Do entirely new particles appear? Does matter undergo a phase transition to a state we have not yet imagined? The equation of state encodes the answer. If we can determine the equation of state precisely enough, we will know what matter does under the most extreme compression in nature. We will know whether quark matter exists in neutron star cores. We will know whether hyperons appear. We will know the maximum mass a neutron star can reach. We will know the boundary between neutron stars and black holes, not just as an approximate range, but as a precise number. And there is a deeper significance still. The equation of state of dense matter is connected to fundamental questions about the strong nuclear force. The strong force is described by quantum chromodynamics, one of the pillars of the standard model of particle physics. But quantum chromodynamics at the densities relevant to neutron stars is effectively unsolvable with current mathematical techniques. By determining the equation of state from neutron star observations, we are indirectly solving a piece of quantum chromodynamics that we cannot solve directly. We are using astrophysics to do particle physics. We are using the cosmos as a calculator. The picture that is emerging from all these observations and calculations is nuanced. The equation of state appears to be moderately stiff. It must support at least 2 solar masses, which eliminates the softest models. But it cannot be infinitely stiff, because that would violate causality, the requirement that the speed of sound in the material cannot exceed the speed of light. The radii measured by NICER suggest it is not extremely stiff either, since extremely stiff equations of state would produce neutron stars larger than what is observed. The truth appears to lie in a middle ground. The equation of state is stiff enough to make robust, heavy neutron stars, but not so stiff that it violates known physics. This moderate stiffness is itself informative. It suggests that the interactions between neutrons at supranuclear densities are strongly repulsive, more so than the simplest models predict, but not without limit. The matter pushes back hard, but not infinitely hard. There is a ceiling, and that ceiling determines the maximum mass. The best current estimates place the true Tolman-Oppenheimer-Volkoff limit somewhere in the range of 2.1 to perhaps 2.4 solar masses, though the precise value remains uncertain. If a neutron star somehow accumulates mass beyond this limit, nothing inside it can resist the resulting gravitational force. The degeneracy pressure of the neutrons, the repulsive core of the strong force, the contributions of every particle and every interaction inside the star, all of them together are not enough. The star collapses. The matter falls inward, and space-time itself closes around it, forming an event horizon from which nothing can escape. A black hole is born. The Tolman-Oppenheimer-Volkoff limit is not just a number. It is a boundary in nature, a dividing line between 2 fundamentally different kinds of objects. Below the limit, matter can resist gravity. Quantum mechanics and nuclear forces find a way to hold the star up, even under the most extreme compression imaginable. Above the limit, no known force, no known state of matter, no known arrangement of particles can generate enough pressure. Gravity wins absolutely and completely. The collapse is total. The object that results, a black hole, is not made of matter at all in any conventional sense. It is a region of space-time from which not even information can escape. And the position of that boundary, the exact mass at which the transition occurs, depends entirely on the equation of state of matter at densities we cannot produce on Earth. It depends on the behavior of the strong nuclear force at energy scales where our best theories struggle. It depends on whether quarks are liberated from their neutron prisons deep in the core. It depends on physics we are still trying to understand. This is why the equation of state matters. This is why physicists devote entire careers to measuring neutron star masses and radii with fractional precision. This is why new telescopes and new gravitational wave detectors are being built. Every measurement, every observation, every data point is a clue about the nature of matter under the most extreme conditions in existence. A clue about where the boundary between neutron stars and black holes truly lies. And there is one kind of event that tests this boundary more violently, more directly, and more spectacularly than anything else in the universe. An event where two neutron stars collide, where the equation of state is pushed to its absolute limit in real time, and where the outcome, survival or collapse, plays out in milliseconds. That event is a neutron star merger, and it is where our story goes next. A neutron star does not exist in isolation. It lives in a galaxy filled with other objects, other stars, clouds of gas, stellar remnants, and sometimes other neutron stars. And this matters enormously for the question we have been asking throughout this journey, because a neutron star's mass is not necessarily fixed. A neutron star can gain mass, and when it gains enough, the balance that has held it together since the moment of its birth finally fails. There are two main ways a neutron star can accumulate additional mass. The first is accretion, the second is collision. Both are violent, both push the equation of state to its limits, and both have given us some of the most important observational data in all of modern astrophysics. Accretion happens when a neutron star is in a binary system, orbiting in a gravitational dance with a companion star. Many stars in our galaxy exist in binary or multiple star systems rather than alone. If a neutron star orbits close enough to a companion, and if that companion expands as it ages, swelling into a red giant or simply filling its gravitational boundary, material from the companion can flow onto the neutron star. This boundary is called the Roche lobe, and when a star expands to fill it, gas from the companion spills through the gravitational saddle point between the two objects and spirals down onto the neutron star. The infalling material does not land gently. It arrives at velocities that are a significant fraction of the speed of light because the neutron star's gravitational field is so intense. The gas forms a swirling disk around the neutron star called an accretion disk, and as material spirals inward through this disk, it heats up to millions of degrees and emits intense X-ray radiation. These systems, called X-ray binaries, are among the brightest X-ray sources in the sky. We have observed hundreds of them in our galaxy and in nearby galaxies. Over time, the material settling onto the neutron star adds to its mass. Slowly, gram by gram, kilogram by kilogram, the neutron star gets heavier. The process can continue for millions or even billions of years, and as the mass increases, the internal pressure must increase to compensate. The neutrons are compressed more tightly, the degeneracy pressure rises, the nuclear forces work harder. The relativistic feedback, where pressure strengthens gravity, becomes more significant. This is actually how millisecond pulsars are created. A neutron star in a binary system accretes material from its companion over a long period of time. The infalling material carries angular momentum, and as it settles onto the surface, it spins the neutron star up, like pushing a merry-go-round faster and faster. Given enough time and enough accreted material, the neutron star can be spun up to rotational speeds of hundreds of revolutions per second. These recycled pulsars are among the most precisely timed objects in the universe, their pulses arriving with a regularity that rivals atomic clocks. But the accretion also increases the mass, and if enough mass accumulates, the neutron star will eventually cross the Tolman-Oppenheimer-Volkoff limit. The internal pressure, despite everything quantum mechanics and nuclear physics can provide, will not be enough. The neutron star will collapse into a black hole. This has almost certainly happened many times throughout the history of our galaxy, though we have never directly witnessed the moment of collapse. What we would see is an X-ray binary that suddenly goes silent. The pulsations would stop. The X-ray emission would change character as the neutron star vanished behind an event horizon. One moment, there would be a spinning, pulsing, radiating neutron star. The next, a black hole. Quiet, dark, permanent. But accretion is slow. The more dramatic way a neutron star can reach its breaking point is through a collision with another neutron star. And this is where the physics becomes truly spectacular. Neutron star mergers begin long before the collision itself. Two neutron stars in a tight binary system orbit each other, bound by gravity. In our galaxy, such systems exist. We have observed them. The first was discovered in 1974 by Russell Hulse and Joseph Taylor, a pair of neutron stars orbiting each other with a period of about 7.75 hours. This discovery would earn them the Nobel Prize in 1993, not just because binary neutron stars are interesting, but because of what Hulse and Taylor measured. They found that the orbital period was decreasing. The two neutron stars were spiraling toward each other, their orbit shrinking by about 3.5 millimeters per orbit, exactly as Einstein's general theory of relativity predicted. The reason for the inspiral is gravitational wave emission. General relativity predicts that any two masses orbiting each other will emit gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. These waves carry energy away from the system. As energy is lost, the orbit shrinks. The two objects spiral closer together. As they get closer, they orbit faster. As they orbit faster, they emit gravitational waves more powerfully. As they emit more powerfully, they lose energy more rapidly. As they lose energy more rapidly, the orbit shrinks faster. This is a runaway process. It starts incredibly slowly. The Hulse-Taylor binary will take roughly 300 million years to merge from its current orbit. But in the final moments, the last few orbits, the process accelerates dramatically. In the last minutes before a neutron star merger, the two objects are orbiting each other hundreds of times per second. They are separated by only a few tens of kilometers. Their orbital velocity approaches a significant fraction of the speed of light. The gravitational wave emission is enormous, pouring out energy at a rate that briefly exceeds the combined light output of every star in the observable universe. Not in light, in gravitational waves, in ripples in space-time itself. And then they collide. The collision is one of the most violent events in the universe. Two objects, each denser than an atomic nucleus, each containing more mass than the Sun, slam into each other at roughly 1/3 the speed of light. The impact generates temperatures in the hundreds of billions of degrees. Material is flung outward in all directions. Shock waves tear through the merging remnant. The combined object shudders and oscillates violently, its shape distorting wildly as it tries to find a new equilibrium. What happens next depends on the total mass and on the equation of state. If the combined mass is below the Tolman-Oppenheimer-Volkoff limit, a new, more massive neutron star can form. It will be hot, rapidly rotating, violently oscillating, but ultimately stable. It will cool over time, settle down, and persist as a single heavy neutron star. But this outcome appears to be rare, because most neutron star mergers produce a combined mass that exceeds the limit. If the combined mass is above the Tolman-Oppenheimer-Volkoff limit, but only slightly above it, something remarkable can happen. The merged remnant can survive temporarily. For a brief time, perhaps tens of milliseconds, perhaps a few seconds, the rapidly spinning remnant is supported by a combination of thermal pressure from the extreme heat of the collision and centrifugal force from its rapid rotation. Neither of these would be sufficient on their own. Neither would be sufficient indefinitely. But together, temporarily, they can hold the object up against gravity, even though its mass exceeds the non-rotating cold limit. This transient survivor is called a hypermassive neutron star. A hypermassive neutron star is an object that should not exist by the cold, static rules of equilibrium. Its mass exceeds what degeneracy pressure and nuclear forces can support in a non-rotating star at zero temperature. And yet it persists, briefly, because the collision has given it two temporary lifelines. The first is heat. The violence of the merger has heated the interior to temperatures of hundreds of billions of degrees, and at those temperatures, thermal pressure makes a genuine contribution, something that is negligible in an old, cold neutron star, but significant in a freshly forged remnant, still glowing from the impact. The second lifeline is rotation. The merger produces a remnant spinning at close to 1,000 rotations per second. At those speeds, centrifugal effects are substantial, pushing material outward, reducing the effective gravitational compression at the equator, allowing matter that would otherwise be crushed to survive a little longer. But both lifelines are fraying from the moment they are created. The heat radiates away, carried off by neutrinos pouring out of the interior at colossal rates. Neutrinos barely interact with matter, so they escape almost freely, draining thermal energy from the remnant faster than any other cooling mechanism could. Meanwhile, the rapid rotation is being braked by gravitational wave emission. The remnant is not perfectly symmetric. It oscillates, wobbles, develops asymmetries in its shape, and every asymmetry generates gravitational waves that carry away angular momentum. Each wave slows the rotation slightly. Each fraction of a revolution lost reduces the centrifugal support. The hypermassive neutron star is dying from the moment it is born. It is living on borrowed time, propped up by energy it is spending faster than it can afford. Within milliseconds to seconds, the thermal pressure drops below the threshold that matters. The rotation slows below the speed needed to compensate, and then, in an instant, the remnant crosses the true limit. The last shred of temporary support vanishes, and the matter that resisted gravity for those brief moments can resist no longer. The collapse is sudden. A black hole forms. An event horizon appears. The matter that moments ago was a neutron star, matter that had resisted gravity for millions or billions of years before the merger, and then clung to existence for a few desperate seconds afterward, falls behind the horizon forever. If the combined mass is significantly above the limit, the collapse is almost instantaneous. The two neutron stars merge, and the resulting object cannot be supported even briefly. A black hole forms within a millisecond of the collision, swallowing most of the material. Only a small amount of matter around the edges, flung outward by the violence of the impact, escapes the event horizon. The fate of the remnant, whether it survives as a stable neutron star, lingers briefly as a hypermassive neutron star, or collapses immediately into a black hole, depends on two things: the total mass of the merging system and the equation of state. A stiffer equation of state raises the threshold for collapse, allowing heavier remnants to survive longer. A softer equation of state lowers it, causing collapse to occur sooner and at lower masses. This means that by observing what happens after a merger, By determining whether the remnants survived or collapsed, and for how long, we can directly constrain the equation of state. Each merger is not just a spectacular explosion. It is an experiment testing the limits of matter. On August 17, 2017, humanity witnessed a neutron star merger for the first time. The gravitational wave detectors LIGO and Virgo picked up a signal from two neutron stars spiraling into each other in a galaxy roughly 130 million light-years from Earth. The signal lasted about 100 seconds, far longer than the fraction of a second signals from black hole mergers that LIGO had detected previously. During those 100 seconds, the two neutron stars completed hundreds of orbits, spiraling closer and closer, their gravitational wave signal rising in both frequency and amplitude in a characteristic pattern called a chirp. Then the signal reached its peak as the two stars collided, and shortly afterward it faded. Less than 2 seconds after the gravitational wave signal ended, a brief flash of gamma rays arrived from the same region of sky detected by the Fermi Gamma Ray Space Telescope. This was a short gamma ray burst, one of the most energetic types of electromagnetic explosion in the universe. For decades, astronomers had suspected that short gamma ray bursts were produced by neutron star mergers. The August 2017 event confirmed this connection beyond any reasonable doubt. The gravitational waves told us two neutron stars had collided. The gamma ray burst told us what followed. The short delay between the gravitational wave signal and the gamma ray burst, less than 2 seconds, itself carried information. It suggested that the merger did not immediately produce a black hole. The remnant likely survived for a brief time, perhaps as a hypermassive neutron star, before collapsing. During that brief survival, the magnetic fields of the merged object organized themselves, and when the black hole finally formed, a jet of material was launched outward along the rotation axis at nearly the speed of light. That jet, punching through the surrounding debris, produced the gamma ray burst we detected. The timing of the delay, though measured in mere seconds, constrained how long the remnant survived, which in turn constrained the equation of state. But the observations did not stop there. Within hours, telescopes around the world turned to the location identified by the gravitational wave detectors. What they found was extraordinary. A new point of light in the host galaxy, growing in brightness over the first day, changing color from blue to red over the following week, then gradually fading. This transient glow was a kilonova, a phenomenon that had been predicted theoretically but never conclusively observed before. A kilonova is powered by the radioactive decay of heavy elements freshly created in the merger debris. When the two neutron stars collide, a fraction of the material, perhaps a few percent of the total mass, is ejected into space at velocities reaching 10 to 30% of the speed of light. This ejected material is extraordinarily neutron-rich, far more neutron-rich than anything that exists naturally on Earth or in ordinary stars. In this violently expanding cloud of neutron-rich matter, a cascade of nuclear reactions occurs. Neutrons are captured onto lighter nuclei in a rapid frenzy, building heavier and heavier elements in fractions of a second. This process, which physicists call the R process, short for the rapid neutron capture process, is one of the two main ways the universe creates elements heavier than iron. And the elements it creates are among the most familiar and valued substances on Earth: gold, platinum, silver, uranium, thorium, lead. These are not forged in ordinary stars. They are not produced by the nuclear fusion that powers the sun. They are created in the most violent events the universe has to offer, events where matter is torn apart and reassembled under conditions so extreme that hundreds of neutrons can be captured onto a single nucleus in less than a second. The August 2017 kilonova provided direct evidence that neutron star mergers are a major, possibly dominant source of these heavy elements in the universe. Spectroscopic observations of the kilonova confirmed the presence of specific heavy elements in the ejected debris. Strontium, an element with 38 protons, was identified in the spectra within days of the merger. The overall brightness and color evolution of the kilonova matched models that predicted the creation of lanthanide elements, the group that includes some of the heaviest stable elements on the periodic table. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a nuclear reactor. All of these may trace their origins to ancient neutron star mergers that occurred billions of years ago, long before our solar system formed. But for our story, the most important aspect of the August 2017 event was what it told us about the equation of state. The gravitational wave signal from the in-spiral, those final 100 seconds before the collision, carried information about the tidal deformation of the two neutron stars. As the stars orbited closer and closer, each star's gravitational field raised a tidal bulge on the other, distorting its shape slightly from a perfect sphere. The size of this distortion depends on how compressible the star is, which depends directly on the equation of state. A star with a stiff equation of state is larger and more easily deformed. A star with a soft equation of state is more compact and more resistant to tidal distortion. The gravitational waves carry an imprint of this deformation. By analyzing the precise shape of the gravitational wave signal, physicists could extract a quantity called the tidal deformability, which measures how much the stars were squished by each other's gravity. The result constrained the equation of state from a completely new angle, independent of mass and radius measurements. The analysis showed that the neutron stars in this event were not excessively large. Their tidal deformation was moderate, ruling out the very stiffest equations of state that predicted neutron stars with radii of 15 or 16 kilometers. Combined with the mass measurements from pulsars that ruled out the softest equations of state, the gravitational wave data helped narrow the range of possibilities to a remarkably tight band. The equation of state of ultra-dense matter, this relationship that governs how matter behaves at densities beyond anything achievable on Earth, was being constrained from multiple independent directions simultaneously, and the constraints were converging. This single event, one collision of two neutron stars in a galaxy 130 million light-years away, taught us about nuclear physics, about the origin of heavy elements, about the source of gamma-ray bursts, about the equation of state of dense matter, and about the boundary between neutron stars and black holes. It was observed in gravitational waves, gamma rays, X-rays, ultraviolet light, visible light, infrared light, and radio waves. It was one of the most thoroughly studied astrophysical events in human history, and it demonstrated the extraordinary power of what astronomers call multi-messenger astronomy, using multiple types of signals from the same event to build a complete picture. Since that first detection, additional neutron star merger candidates have been identified in gravitational wave data. Each new detection provides additional constraints. Some events appear to involve neutron stars with different masses, probing different parts of the equation of state. Some may involve a neutron star merging with a black hole rather than another neutron star, which provides different information. One event detected in 2019 involved two objects with a combined mass significantly higher than the August 2017 event, raising questions about whether the heavier component might already have been a low-mass black hole rather than a neutron star. These ambiguous cases are themselves informative because they probe the boundary region, the mass range where it becomes unclear whether an object should be a neutron star or a black hole. This boundary region is one of the most fascinating areas in astrophysics. We have observed neutron stars with masses up to about 2.1 solar masses. We have observed black holes with masses as low as roughly 5 solar masses. Between approximately 2.5 and 5 solar masses, there is a gap, a range of masses where very few objects have been confidently identified. Is this gap real, or is it an artifact of our limited observations? If it is real, why does it exist? The equation of state determines the upper edge of this gap. Whatever the maximum neutron star mass is, objects heavier than that must be black holes. The lower edge of the gap might reflect the physics of how black holes form in supernovae. Perhaps the core collapse process tends to produce either neutron stars below the Tolman-Oppenheimer-Volkoff limit or black holes above 5 solar masses, with few objects in between. The explosion dynamics might not easily leave behind remnants in the intermediate range. Or perhaps objects in the gap exist, but are difficult to detect because they are quiet, not actively accreting or emitting radiation. A black hole of 3 solar masses sitting alone in space, not consuming any material, would be essentially invisible. It would curve space-time around it, but it would emit no light, no radiation, no signal of any kind. We would have no way to find it unless something happened to pass nearby. The gap might be populated with silent black holes we simply cannot see. Gravitational wave detections are beginning to probe this gap. Every merger event that involves objects near the boundary contributes new evidence. If future detections reveal objects confidently sitting inside the gap, it would transform our understanding of how compact objects form. If the gap remains stubbornly empty, even as our observations improve, it would tell us something equally profound about the physics of stellar death and the limits of matter. Future gravitational wave detectors will help answer these questions. The current detectors, LIGO and Virgo, along with the Japanese detector Kagra, are being upgraded to greater sensitivity. But the truly revolutionary step will come with the next generation of detectors. The Einstein telescope, a proposed underground detector in Europe, with arms 10 kilometers long arranged in a triangular configuration, would be roughly 10 times more sensitive than current instruments. Cosmic Explorer, a proposed detector in the United States, with arms 40 kilometers long, would push sensitivity even further. These instruments, planned for the 2030s, would detect neutron star mergers not in the nearby universe, but across cosmological distances, observing hundreds or even thousands of mergers per year compared to the handful detected so far. Each merger provides another measurement of tidal deformability. Each measurement constrains the equation of state further. With hundreds of detections, physicists could map the relationship between pressure and density inside ultra-dense matter with a precision that would have been unimaginable a generation ago. They could determine whether quark matter exists in neutron star cores. They could resolve the high-Perron puzzle. They could pin down the maximum mass to within a few hundredths of a solar mass. The equation of state, this single relationship that governs what matter does under the most extreme compression in nature, would finally be known. And every one of those measurements brings us closer to answering the question we started with. What keeps a neutron star from becoming a black hole? The answer, as we have seen across this entire journey, is not simple. It is not one thing. It is a layered, interlocking resistance built from some of the deepest principles in physics. At the foundation is the Pauli exclusion principle. Neutrons are fermions. They cannot share quantum states. As gravity compresses the star, the exclusion principle forces neutrons into higher and higher energy states, generating a pressure that resists further compression. This degeneracy pressure would exist even at absolute zero. It is not thermal. It is quantum mechanical. On top of that foundation is the strong nuclear force. At the extreme densities inside a neutron star, neutrons are packed closer together than they are inside ordinary atomic nuclei. At these distances, the strong force becomes repulsive, pushing back against compression with enormous intensity. This nuclear repulsion adds critical stiffness to the matter, allowing neutron stars to exist at masses far above what degeneracy pressure alone could support. Woven through everything is the complexity of ultra-dense matter itself. The precise mix of neutrons, protons, electrons, and possibly hyperons or free quarks determines how much pressure the material generates at each density. These details, encoded in the equation of state, control the maximum mass a neutron star can sustain. And complicating everything is general relativity. In Einstein's theory, pressure itself contributes to the gravitational field. The very thing that holds the star up also makes gravity stronger. This relativistic feedback loop means the balance between gravity and pressure is more precarious than it would be in Newtonian physics. The margin for survival is narrower. The maximum mass is lower. All of these effects conspire together to create an object that exists on a knife edge. A neutron star survives because the combined resistance of quantum mechanics, nuclear physics, and the behavior of matter at extreme density is, for that particular mass, just barely enough. Add a little more mass, push the density a little higher, strengthen the gravitational field a little further, and the balance tips. The resistance that held for billions of years collapses in milliseconds. The neutron star crosses its event horizon and becomes a black hole. This is what makes neutron stars so remarkable. They are not just dense objects. They are not just exotic remnants of dead stars. They are tests of fundamental physics, conducted on scales and under conditions that we cannot achieve in any laboratory. Every neutron star that exists is proof that quantum mechanics and nuclear forces can resist gravity up to a certain point. Every black hole that exists is proof that beyond that point, they cannot. And the exact location of that point, the precise mass at which resistance fails and collapse becomes inevitable, encodes within it the answer to one of the deepest questions we can ask about matter. How does the stuff the universe is made of behave when it is compressed as far as nature will allow? We do not yet have the complete answer, but with every neutron star we weigh, every radius we measure, every merger we detect, every gravitational wave signal we decode, we get closer. The neutron star is not just an object to study. It is a message from nature, written in the language of density and pressure, telling us what matter can endure before it breaks. And when it breaks, when gravity finally overwhelms every form of resistance that physics can muster, something extraordinary happens. The matter does not merely compress further, it disappears. It falls behind a boundary from which nothing returns. Not light, not information, not the memory of what the object once was. A neutron star, with all its complexity, all its layered physics, all its quantum mechanical stubbornness, ceases to exist as a material object and becomes something else entirely. A black hole. A region of space-time curved so severely that it seals itself off from the rest of the universe. That transformation, from the most extreme form of matter to the most extreme form of space-time, is perhaps the most dramatic boundary crossing in all of nature. And it is governed, ultimately, by a relationship between pressure and density that we are only now beginning to measure. The equation of state of ultra-dense matter, the rule that tells us how hard the universe pushes back when gravity tries to crush everything into nothing. We have built telescopes in space and on mountaintops. We have constructed gravitational wave detectors that can measure distortions in space-time smaller than 1/10,000th the width of a proton. We have observed collisions between neutron stars in galaxies more than 100 million light-years away. And all of this effort, all of this ingenuity, all of this technology is directed at answering one deceptively simple question. What keeps a neutron star from becoming a black hole? The answer is everything quantum mechanics and nuclear physics can throw at gravity. And the most extraordinary part of the story is that sometimes for the heaviest neutron stars, for the most violent mergers, for the most extreme densities in the known universe, everything is not enough.